Hi everyone. Today we're going to be discussing exercise 5 of our assignments, and this is related with comparing the baseline, the current water management versus alternative strategies. So let's start exploring this. So the first part, this I'm explaining how it was estimated the climate change data that you're going to be using on your report. So basically here, you can see that we went to this tool that is called CanAdapt. And then here we took a look at this climate change snapshot. When you do that, you have to select the location where you want to extract the data. In this case, what we did is went here to this part of Monterey Bay and select this region that is close to Watsonville. Once you generate a snapshot, then you can select precipitation and non-precipitation. So here precipitation, and here you can have annual precipitation, and you can see this variability. What will be the variability? What is the observed data? And then here we have two emission scenarios. One that is the medium emission, the RCP 4.5, and the high emissions. And basically this data was used, and then it was later, it was used to generate some with stochastic modeling, a time series data that you will able to see here. So here you can see the different traces, so the different possibilities that you can have for precipitation in a medium emission scenario. So you have 10 different traces, 10 possibilities, and also in a high emission scenario, which that will be also another 10 possibilities. Notice that to select any of these traces, any of these possibilities, for the low emission, you have to select the number from 1 to 10. And then similarly for a high emission scenario from 11 to 20, okay? Now, we did exactly the same, but now using temperature as a proxy. And then in here in temperature, you can see temperature and annual maximum temperature. Annual average maximum temperature, and you can see what will be the different possibilities. In this case, we use the same stochastic model here. That in order to generate the time series data and also the different monthly variabilities. So this is what you're going to be seeing here in climate change. So these tabs are named CC because it's climate change, and then the underscore reference evapotranspiration, or CC underscore precipitation for precipitation. Now, what we're going to do is to take a look at the current management scenario comparison. And here you can see that we already have data for the baseline scenario. So this is the total water demand for the baseline scenario. Then here we have the total water use for the baseline scenario here. And then finally, we also have the aquifer storage for baseline scenario. So this, you don't have to delete it. You basically, what I did is I already had some results for scenario 1, but you can see that here are the baseline results already for you for the total water demand. This come already from this water budget. When you were doing the baseline scenario, that's where I was obtaining that data there. And here we're going to copy the total water demand. We're going to be also copy the total water supply and also the aquifer storage for the different scenarios that you're going to be evaluating. Now, in terms of documentation practices, what I recommend is that you will have to set the date, who is doing it, what is the number of the scenario, and that you provide a description of what are you doing with the scenario. So this scenario evaluates the impact of climate change for high scenarios. The objective is to evaluate climate change, right? Variables, I'm going to change this variable in cell 2, and I'm going to change it to number 11. And to test one realization of climate change for RCP 8.5. The rationale is that climate change is already happening, thus it's important to understand the impact of climate change. This is my references. I use this data from Canada and the aquifer, and then we're going to analyze the results. So here is one example. So for instance, in this one, well, here I change it to number. Let's evaluate this one, okay? Well, actually, before no, let's just go ahead and evaluate it. So here in dashboard, I'm going to here cell C2, and I'm going to type 11. So basically, what it says here is that if this cell is 0, it will be the historic climate data. From 1 to 10, it will be low emissions scenarios. And so any number from 1 to 10 will provide you a realization from the low emission scenarios, and any number from 11 to 20 for high emission scenarios. So I want to start with one of the high emission scenarios. And that's what I was documenting here. So this is the date, my name, the number of a scenario. I change this cell to 11, and then I'm providing this. Now, in terms of what is happening, you're going to see that here to your left, this one, this provides a snapshot of the results. So here you can see the aquifer storage, the total demand, and the water sources. How the red line is my scenario, so it's what you're changing, and then the blue bars are the baseline results. So you can see here that climate change, without doing anything, we're going to have less aquifer storage because of climate change. In some years, the water demand will increase, and some years will have higher water supply, but in other years, we will have lower water supply. So it's bringing us to these extremes. So basically here in the scenario description, that's what I'm writing out here. This aquifer storage for scenario 1 is lower than the baseline. It is expected that climate change will reduce aquifer storage. It is also expected a higher variability in water sources and increased water demands. So that will be the key results, right? So this is how I'm documenting the strategy. Now, once we have all of this, what we need to do is to copy the total water demands, the total water sources, and aquifer storage from this water budget tab into the scenario comparison. So here, what I'm going to do is copy this total water demand, and then I'm going to put it in here in the scenario comparison. Then the total water sources or water supply. And finally, I'm going to copy the aquifer storage from here. So now, not only I have the description of my exercise of this scenario, but also I store the data for the key results where I can compare the aquifer storage, then the total water demand, and the total water supplies. Now, let me actually explain you what is in the dashboard. So in here, basically there are different sections. This first section here, that is in this pinkish color, is climate data inputs, and this is what I was explaining. Basically, you can have it in here for change this value, and it will allow you to estimate historic, or it can be one realization for low emission, or another different realization for high emissions. Now, the urban water management are this orange color, and basically what you're going to see is this is extremely similar of what you did on your exercise number 2, and this will be to test different urban or rural water management strategies, and this is the implementation timeline. Then for agricultural water management, we have a section in green, and in this section in green, you're going to be changing different values, columns, so you can change the strategies that you want to test for agricultural water management. Increase water supply, there is a section in here for increased water supply, and you can change a lot of this in here. And finally, quick summary of results, and this quick summary of results is in here. And basically, this is some of the screenshots that you're going to be turning in for this class. So let's just do one. So, well, this one I changed it already for 11, and then you can see the different results. So this is what I was doing here. I changed this to 11, and if you remember correct, this is some of the results that we had here. You can see the results now in here, right? Now, change the idea is that you, well, here to be turned in is you have to change now one here in the dashboard and evaluate another climate change scenario, another climate change trace. Let's do one super fast. So now I'm going to change it to number 1. So here I will go to the scenario description, and then in here what I'm going to say is same date, same author, scenario number 2. This scenario will evaluate the impact of climate change, but in this one, I'm changing it to, to number 1. So number 1 is low emission scenario, an RCP 4.5. So this is going to be low emission scenarios here. In C2 of the dashboard to series number 1 to test a low emission scenario. Climate change is already happening, and now what I need to know is what are the key results. So in here we'll go to our and you can see that it is the same. Well, we're going to have about the same storage at the end, but it is still overdraft. What that means is that we're still doing an overuse and exploitation of groundwater resources. Here you can see the 3 of them, basically, which is how these total water demands are changing. Here we have the same, sometimes way too much water, sometimes very lower than what typically happens. So we can say in here something very similar, which is that the storage, the aquifer storage in scenario 2 is about the same as the baseline scenario. but still in overdraft conditions. It is expected that climate change will reduce. This is no longer the same, but it will be, we will have about the same. It is expected that high variability in water sources and increased water demands. So that will be our results for that. So now that we have changed here our climate change trace to 1, what we're going to do is to go back here to water budget and copy once again the total demand to scenario comparison. And now the total water supplies, which is this. And last but not least will be the aquifer storage. So now you have all your variables already stored for this to compare two different types of climate change data. Now, what you will have to do in the following part of the exercise is, now let's go back here, and I will put it again in this. So you will have to evaluate 3 individual scenarios and considering medium and high emission scenarios. So 3 individual scenarios times 2 climate change, so you will have to evaluate 6 scenarios. One scenario should be for urban and water management, so for this section in orange. One individual scenario for agricultural water management, so one will be here in the green section, and one for increased water supply, which it will be here. So you will only change one variable and then see how it works. You have to change one variable in here or one of your strategies and modify this to one climate change scenario. So one will be low emissions, so from 1 to 10, and another one will be high emissions from 11 to 20. Make sure that you have this description. Also make sure that you copy and paste these figures. For each scenario, you have to provide the rationale why you're doing it. Basically, you can copy and paste this, and as you're doing it, provide the variables that you change, what is your rationale, the citations, and key results. And you have to discuss what are the economical or social implications of these strategies. So how we're going to pay for these strategies, who is benefiting it, who is not. Who is the individual that may be affected, and so on. At the end, once you have finished these 6 scenarios, you will have to provide a summary of the graphs of the total water demand, total water sources, and aquifer storage. Once you have all the 6 scenarios evaluated in here, so basically what you're going to have is all the way up to here, you will have also the time series data for the water demand, the water supplies, and the aquifer storage for 6 more scenarios. And what you will do is to create a chart where you are comparing these 6 or 8 scenarios compared to the baseline and see how those are different, what are the different possibilities of each of these individual scenarios, and how will they compare with the baseline scenario. Now let's go back here and go back and change our trace to 0, climate data input to 0. And right now, yeah, things should be exactly the same. Our scenario should look the same as the baseline results. Okay, let's explore what are some of the options that you can do for your ideas for urban water management. Here there are some ideas, so you can change the appliance efficiencies. And what you can see here for laundry and dishwashers, we have right now these efficiencies, right? If you remember, we estimated those here using, so this value, this 6.4, came from, oh, I see. Right now that one is changed, but here you can see that, for instance, we can go, this is 6.4, right? But we can go to one that is really advanced, that it can be 4.5. So basically here we can change in our dashboard to this one to 4.5, if this will be a very advanced. Also for the dishwasher, we can change this once again. Right now, if I remember correct, we have a 4.7. So we can go all the way to a high efficiency that can be 2.6. So we can go back to the dashboard, change these ones on the dashboard to 2.6. So that will be modifying these values, and you can do it on the urban or in the rural and change it to higher efficiency. Now for faucets, I mean right now it's 2 gallons per minute, but there are some faucets that actually have can have lower water rates, flow rates, instead of 2 to 1.5. So this one, here we change it instead to 1 gallon to 1.5. And that also, we can change one. For the shower heads, here we have some of those that can, instead of be 2, can go all the way to 2.5 or even to 1.25. So this, we can change it to 1.25, or the toilets, which some of those, they are now 1.28 gallons, which that will be, instead of 2.2, this will be 1.28 gallons. You can change it here for urban or rural. Now this will be in terms of changing the efficiency or changing the all of these efficiencies, or you can change the behavior, which is how many, instead of 10 minutes, 8 minutes, faucets using less water in here. Now in terms of increased water supply, you can also consider rainwater harvest or reuse of gray water. So for rain harvest, you can go to this applied water, and then in here we have the precipitation that happens on average on Pajaro Valley. So what we can think is that we have a roof that is 700 square foot, and that we're collecting this average precipitation on that roof, basically by multiplying this, which is the precipitation, times the square footage. This is a conversion factor. So basically this converts from cubic feet to gallons. So in this case will be this over the cubic feet. So we're collecting about 197 gallons on a year. We divide these gallons over 365, that will be the per day. And we divide this over 4 people. And this is how much gallons per person you can save per day on average, right? So you can basically go back here to the dashboard, and yeah, you can use this value to reduce the water demand per capita. So in here at the end, what you can do is you can say minus, and then you can go back here to this applied water and select this value that will be 0.13. And here you will be considering so all what you're having in here, but then this part will be by collecting water. You can do it in that way. You can also what you can put it in here outdoor. You can use rainwater harvesting. Well, you should take a look at this residential conservation webpage and all the things that they are doing. Oh, before I forget, also here on the increased water supplies, you can also do the reuse of the gray water. So basically here in this cell, so what you can do is to also consider rainwater harvest. Here, just type it. And there in this cell, you can call the quantity that we've been estimating. And then at the end, subtract basically this value, this sum of these two outdoor and indoor minus the water that will be rainwater harvest per person, right? Now, the one other thing that you can do is reuse of gray water. I'm just gonna not add the rainwater harvest, but in this case, what I'm going to do with the reuse of gray water is consider that the water from the laundry is reused in the outdoor. Basically, what we need to do is to subtract the laundry use from the total water use. In this case, it will be from here. In this cell E50, sorry, in the E53, which is this guy here, we should subtract, I'm just using this equation, cell G22, this one here, which is the amount of water used in this case for laundry. So this is how much is used for laundry per person per day. And that will give us a reduced water use, but that is because you are reusing water and reusing the laundry into the garden, into the outdoors. So that can be also a different way to do this. Now, for the outdoor, you can change different things. So change the landscape design from non-native, more water intensive to a less water intensive, typically native. And in this case, in here, in this cell E34, what you can do is you can change it to different values. Right now, we're in 0.8, which is this high water use. But we can change all the landscape to plants that are more native, so low or very low. So let's say that here we change it instead of 0.8. We can do it to, let's say instead of rather than 10 or to 30%, so 20%. So this will reduce our outdoor water use. And if you look at glucose, which is, I think this one, here it will explain you the categories of different water needs. So basically that's what you're gonna be doing in there. Okay. Also, you can change to zero landscape. So let me just go back here to 0.8. Now, in terms of zero escaping, what you can do is changing it to no water use at all. So basically that, to type in this place 0, so there will be no water for that one, or that will be zero escaping, or you can also do changing the irrigation efficiency. So here, rather than having a 70% efficiency, that we have a 90% efficiency. So we're gonna use now less water in there. So these will be some of the scenarios for urban and rural, some of the things that you can change for your run scenarios. Also notice here that when you change it, let's say, let's go back to our high emission scenarios. You saw that it took some time, but basically, even though with the same condition as the baseline, the indoor may not change, but the outdoor use will change because we have higher temperature, higher evapotranspiration. So this will be that even though you're not doing anything, it's already worse than the baseline scenario. This is the high emission. If we go back to the low emission, something similar is happening. You can see that the same we have increased water use for this. So let's go back and change it here to 0, just so we know that we are just modifying one variable at a time. Sorry, here should be 0. Yes. You see that it takes some time to recalculate. So here it will look a green bar. So let's say I change it to once again 11. And you can see that in this corner is thinking. So now we change to that value. So I'm going to leave it right again back in 0 so we know that we are just modifying one variable at a time here. Also, another thing that you can change here is what is the timeline that you are implementing these scenarios. So for instance, here we're considering that after 2020, in 2020 there's not going to be any adoption, but here we are 20% in the first year, 40, 60, 80. So it's not that you can change all of them at the same time. Here you can think about what will be the percent of adoption for actually going on that time. You can go all the way to, this year and start changing it from here. And here you're saying that at the beginning, the percent of adoption was 0 until, let's say, for instance, we start here at 20%, 40%, 60%, 80%, and so on. So you can change it accordingly of how you're thinking this is going to be implemented through time. And as I went back and just changed it back to the values, the baseline values. So we're just changing one variable at a time, but I'm just explaining you all the different things that you can change. Now, for the agricultural water management, there are two things that you can do. So take a look at this one, which is basically this link will bring you to this specific web page where you can see some of the things that PBWMA are using for irrigation efficiency. Basically, they are providing efficiency evaluations, rebates for technical assistance, and irrigation scheduling optimization. But basically what you can do here is change your irrigation efficiencies. So for instance, in here, let me just go back here. So going back again to our historic scenario, and then here you can consider that, for instance, we're going to change all of the ones that were 75 to an 85% efficiency. And this one that was already 85 to 95%. And basically what this will do, you have to mention what it will do. In this case, you can see that it reduced the water demand, but also because all of this water that is inefficiently used goes back to the aquifer, also the water sources went down. So basically, we're going to have the same water storage. Because basically, you're not saving water, you're just kind of being more efficient from point A to point B, but not saving any water at all. The other part that you can do, is to modify the acreage. So basically here, you can change the time series data. So you can say that this is the expected land use, this many acres in inland use, but you can increase it so you can have 120%. And you can see how this impacts the. So we have now greater water demand, and most likely we're going to have a smaller water storage. Sorry. But you can do that for all the different uses. You can actually also reduce the land use, right? So let's say that we want only 75% of these, and actually we're going to reduce all of them, all of the agricultural acreage to 75%. And I'm doing this right now for those that are, I think these are inland. Then I can do all of them also for the coastal. There we go. And you can actually see how that one goes. Definitely the water demands have been reduced. Some of the water sources, and we are seeing some recovery here on the aquifer storage. So yeah, you can also do that. What I'm going to do is to now bring back everything to 100%. So we go back to our reference scenario. There we go. And finally, for the water supply augmentation, what you can evaluate are 3 different strategies. So let's go to the first one, which is this increased recycled water use. So what you're seeing here, this time series data is the projected demand for the city of Watsonville that it is in here. So this is from 2008 until 2020. That is that time series data. So 78.99. So you can see it in here. So this is the time series data and the recycled water that is being used in this case for this period of time, right? On average, here we know that they are using lately this much water. Now, this is historically what they've been used in their recycled water. Now, what we're going to do here is these cells here, which is basically that you're dividing the total water use over the recycled water, cannot be greater than 50%. This 50% is how much water is this percentage here. So how much of the water use per capita is actually indoor and outdoor. So the total demand, at least 50% is indoor, and that is the indoor water that will go into the treatment plant of Watsonville that we can get out as recycled water. So one way to estimate or to add some recycled water use is to increase this amount. Basically in here, in these cells, I'm providing you a time series data that you can paste in here. And what you can see here is that this percentage is meeting this value of 50%, less than 50%, and it is increasing the amount of water that is recycled. For instance, if here let's say I have 500 acre feet, it will say that it is not possible because you are recycling a higher percentage of the water used that it doesn't come from indoors. So that water cannot be recycled because that water above this percentage was used outdoors. So that's why I'm having here 100, but you can actually go on, for instance, let's say 200, 150, 140. So that will be possible, right? This time series data that I'm providing you here is a good start, so you can actually change it and see how can you increase the use of recycled water in here. Now, what we're going to do is to go back here and change this to 0. And sorry, just so you can actually see that is, you can come back here and see what is happening with our, you can see that, yeah, that augmented water, it's definitely not reducing the water demand, but it is increasing our water sources a tiny bit. Just consider that the total water use is 48,000, 42,000 acre feet, and this is we're just adding 100 to 1,000 acre feet per year. Okay, so the next one is increased managed aquifer recharge, and basically here, this facility that is called Harkin Slough can recharge water into this facility. Sorry, for the recycled water, you can take a look at this website, and it will tell you where is the treatment plant and how all the different purple pipelines, these recycled water use facilities, are located. For the increased aquifer recharge, you can see the project here of Harkin Slough and how this water is extracted from the slough and then put it into this recharge basin. So you can infiltrate that water into the aquifer. Here it says that you can recharge between 1,000 to 2,000 acre feet only during wet years. So in this cell, you can propose that when there is a wet year, you're gonna have 1,000 acre feet recharge only during wet years, or you can say like up to 2,000. And this will also increase the water use, and you can see here the total increase in storage on augmented water supply. So you can change that value from here. And the last one is that they are here in this College Lake. Basically, they are going to store about 1,000 acre feet up to 1,700. So what we're going to do here is to identify how much of that, so it's between 1,800 to 2,300 per acre feet. So in this cell, you can add any of these two values. So let's start with 1,800. So now this says that every year this water will be stored and used there. But we can think that, for instance, in dry years, only can store, 50% of that. In moderate, so we can do something like that. Moderate, we can say 75%. And in wet years, 100%. Now we can do this manually. Also, we can say here equal if this is dry, and this is equal to dry, then this will be 0.5 or 50%. And then we can have another if this is equal to moderate, then 75, otherwise 100. We close the two ifs. And actually we can put it in here 50%, right? Well, basically it is just putting this in as if they were percentages. So, so we can paste as formulas. Oh yeah, it is doing that. There you go. So basically it's calculating those based on this. So anytime that it is a wet, it is putting 1800, which is 100%. When it is dry, only 50% and so on. Or you just can just keep it as it was before. Sorry, let's change this number to, okay, here. Actually, we can do this. Might be easier. There you go. So we can have all of them as 100%. And it can have it like that. You can also consider that every year you will store this 1800, and you can always come back here and see how much of that is actually affecting at the end the scenario. Now remember that for this, I just explained how each of these scenarios works. You will have to first in here test 3 individual scenarios, and for each of these individual scenarios modify the climate variable here. Sorry, I'm just going to put here 0. So modify this one for testing one individual scenario in combination with this climate variable, and this will be one for urban, one for agriculture, and one for augmented water supplies. And then once you're done that, then you can start having or working on meta scenarios, which basically what it will do is to modify or change a lot of these variables to so do a combination of different scenarios and see how they are affecting it. Remember that you have to, when you have all the scenarios, to create this summary of those individual scenarios by creating a graph. What are the greater benefits of each scenario, and some of the discussions of these individual scenarios, and the same as summary graph of the 3 meta scenarios that you're analyzing with the 2 different climate change values, the graphs, what are the scenarios are providing greater benefits, if the current groundwater is sustainable or not, how would you define a sustainable groundwater management, and you can take a look at this document, which basically, I'll update it in terms of what is the sustainable groundwater management and sigma, and what are the limitations. So, and for some extra points here, discuss socially and environmentally responsible sustainable groundwater management. In this case, who is the individual sector or economic activity that will be benefited? Are there benefits or drawbacks equally distributed? And how would you engage stakeholders in this? Thank you. Thank you for watching this.